We learned to compute determinants using cofactor expansion, but we saw that this could be not so efficient if we have large matrices like 10 by 10 or 20 by 20. We saw that this method asks for a lot of computation and a lot of time. So we have some other options that we can use if we wish, especially when matrices are large. One of the options is to use elementary row operations or column operations to transform the original matrix into an upper triangular matrix. The idea here is that the upper triangular matrix is a matrix that has zeros below the main diagonal, and we know that determinant of such a matrix is actually equal to the product of the entries on the main diagonal. So it's very simple to compute determinant of upper triangular matrix. Now the only thing is we need to see what is the link between determinant of upper triangular matrix that we obtained using these elementary operations and our original matrix. So that's something that needs to be discovered. And another option would be something that is a mix, like hybrid approach, where we can combine cofactor expansion with some useful elementary operations for each matrix that we need to compute determinant for. So it's something that we will examine. This could be useful especially when we try to compute determinant by hand. So at the end of the day, you can choose the option you like. It's your choice, and you are the one computing. So you have three options: cofactor expansion, and the two new options that we are going to see now. And at the end of the day, you will be the one choosing the option you like the most, and or the option that is most appropriate in your specific situation. So we saw that new options that we have will involve elementary row or column operations. So by now we know that determinant of A and determinant of A transpose is the same. So whenever I do something on rows, I could do the same thing on the columns when I'm computing determinant of the matrix. So the big question is, what's the effect of elementary row or column operations on the determinant? So let's see. We have three elementary row operations. So first one is a swap. We swap two rows or we swap two columns. So we have our matrix A, and then we swap two rows, and then we get matrix B. So B is a new matrix. The result says that determinant of a new matrix, B, is equal to minus determinant of the old matrix, A. So each time I do a swap of two rows, determinant of a new matrix is minus determinant of the old matrix. I could do the same on the columns, the same result holds. Another elementary row operations is multiplication by a scalar different from zero. So I have my matrix A, and then I apply elementary row operations where I replace a row by some number, let's say 5, times a row, let's say row 2. So I replace row 2 by 5 times row 2. That's how I get another matrix B. So my new matrix, its determinant is equal to K, the number I chose, times the determinant of the old matrix. So each time I multiply a row by a number, determinant of a new matrix is equal to the number times the determinant of the old matrix. Same thing holds for the columns. And the last operation that we use the most actually is replacement. So I start with my matrix A and I replace a row by that row plus some multiple of another row, and that's how I get a new matrix B. So determinant of new matrix B is equal to determinant of the old matrix A. So the elementary operations that we use the most, the replacement, does not change the determinant. This is beautiful because we are going to use this elementary row operations a lot. We could do the same operation with columns, determinant would not change. So this one is the most used and doesn't change determinant. That's a good news for us. From these observations, we have some properties. If I have a row or a column of zeros in my matrix, determinant is 0, because I can expand by any row or any column. So I would choose a row full of zeros. If I have two rows or two columns that are equal, so the same numbers at the same places, then determinant is 0. If I have two rows or two columns that are proportional, which means that one of them is a scalar multiple of the other, so then determinant is 0 again. So these are things that we can remember and use in our process that will help us simplify the computations. Now, from what we observed with multiplication, elementary row operation, there is an observation to have here. If I have my square matrix A and I obtain B by multiplying the entire matrix A by a fixed number, let's say 5, then the determinant of the new matrix is equal to K, the number I chose, so the 5 in our case, to power size of the matrix times determinant of A. So let's say I have A 7 by 7 and I choose K 5. So I have my matrix A 7 by 7 and I multiply it by 5. So I multiply every entry by 5. That's how I get matrix B. Now determinant of B will be 5 to power 7 times determinant of A. So that comes from the result that we had about multiplication. Here is one row at a time. You multiply by K once. But in our case, I have n rows, so I multiply by K row 1, and then row 2, and then row 3, and then row 4. So that's why we have K to power the size of the matrix. Similarly, if I perform several swaps of rows or columns, so I start with A and I perform certain number K of swaps of rows or columns to get my matrix B, while determinant of B, a new matrix, will be minus 1 to power number of swaps times determinant of A. This is obvious because each swap multiplies determinant of A by negative 1. So if I have 7 swaps, I'll have negative 1 to power 7 here. If I have 2 swaps, it will be negative 1 to power 2. So an example, here I have a 3 by 3 matrix A, and I produce matrix B by multiplying A by negative 2. So this is my matrix B. So I have A and get B by negative 2 times A. Determinant of B will be negative 2 to power 3 determinant of A. Because each time I multiply a row by negative 2, I multiply the determinant of A by negative 2. So I multiply row 1 and row 2 and row 3. So it's negative 2 times negative 2 times negative 2 times determinant of the old matrix A. So I can compute determinant of A, it's negative 12, so determinant of B will be just negative 12 times negative 8. In this example, I have my matrix A, and then I have a sequence of row swaps and column swaps. The order in which they appear doesn't matter, it's just how many of them there are. Here I have 5 swaps, so I started with matrix A, and I performed these 5 swaps, and I got my matrix B. And then we know the determinant of B will be negative 1 to power 5 number of swaps times determinant of the old matrix. In this example, we have something that is approaching the situation that we have normally when we try to produce zeros below the leading entries. So in our quest to produce upper triangular matrix, we will be applying elementary row operations in order to produce zeros below diagonal entries. So we will have most of the time the replacement operation, but sometimes we need to swap rows or columns, and sometimes we need to multiply a row or a column by a specific number to simplify the expression. So let's suppose I have my matrix A, square matrix obviously, and then I perform this sequence of elementary row operations in order to get matrix B. Now, what is the determinant of matrix B? Well, it is some number times the determinant of matrix A. So what's the number? How do I get it? Well, I just follow the operations and multiply the determinant of the old matrix by appropriate numbers. So, first operation was replacement on a row 2. So we know that replacement doesn't change the determinant. So the multiplying factor is 1. Then we had row 3 replaced by 1 over 4 times row 3. We know that when that happens, the determinant of A will be multiplied by same factor, 1 over 4. So that's where we have it. Then for some reason we had to perform a replacement on a column 3. While the replacement doesn't change the determinant. So the multiplying factor is 1. Then we performed multiplication operation on a column 2. So column 2 was replaced by 7 times column 2. We know that determinant of old matrix will be multiplied by 7 also. So that's where we have it. And then we swap to row 2 and 4, while each swap multiplies the determinant of the old matrix by -1. Then we have replacement on a row 5. Replacement doesn't change the determinant, so multiplying factor is 1. Then swapping column 3 and column 4. Each swap of rows or columns is multiplying the old determinant by -1. Here we have it. And the last operation was a replacement on a row 1. Replacement doesn't change the determinant, so the multiplying factor is 1. So the determinant of the new matrix obtained by this sequence of elementary row operations is, so the determinant of A is equal to the determinant of A times all these numbers. So technically it's just 1 and -1 and the multiplying factors for multiplication operation. So all I need to do is just do the product, so I get 7 over 4. So the determinant of B is actually 7 over 4 times the determinant of A. Obviously, the determinant of A is equal to 4 over 7 determinant of B, so you're able to do the math. So that's how normally we would do. We start with A, we apply a sequence of elementary row operations to get the matrix B, and the link between the determinants is determinant of a new matrix is equal to some number times the determinant of the old matrix. And this is how we find the number. Just follow the elementary row operations that we performed. So in the situation when we want to get an upper triangular matrix, so we want to compute the determinant of A, but A is an ugly matrix, has a lot of non-zero values everywhere. So this strategy is to produce an upper triangular matrix using elementary row operations. So why do we want upper triangular matrix? Well, we remember the result that says that upper or lower triangular matrix or a diagonal matrix, well, the determinant for those matrices is very easy to compute. It's just the product of entries on the main diagonal. So that's why we like it. And we now learned how to link the determinant of a newly obtained triangular matrix with the determinant of our original matrix. We just need to follow the sequence of elementary row operations. So it's called, the method in the book is called row reduction, because basically what we do is introducing zeros below the leading entries. In this case, we can use any elementary row operation we like. We can use them on rows or columns as we like, it's fine. We just need to keep the list. And this will help us transform our original matrix into a cute upper triangular matrix. Or you can transform it also in a lower triangular matrix, it's up to you. In any case, lower or upper triangular, determinant of lower or upper triangular is just the product of the entries on the main diagonal. So that's why we do all this, because the determinant of triangular matrices is super easy to compute. And the last step is to follow the sequence of these elementary row or column operations that we used to start to transform A into B. So that will help us establish the link between determinant of A, our old matrix, and determinant of B, our new cute triangular matrix. So here is an example. I have a 3 by 3 matrix here, and I need to find determinant. So I could use cofactor expansion, it's fine, but I want to illustrate the use of elementary row operations here. So what we do normally, we would try to produce 0 below the leading entry, so 0 below the leading one, so we want these two zeros. So what do? I transform matrix A by using the replacement elementary row operations, these two. So I get this matrix B. Obviously A and B are different matrices. We know that. But we also know the determinants are linked, and the link is determinant of B will be determinant of A times certain number depending on these elementary row operations. Here we performed replacement. We know that replacement doesn't change the determinant. So I know already that determinant of this matrix A, original matrix, and determinant of matrix B is the same, because we applied replacement operations. Now matrix B, if we check, is not actually triangular. I would swap row 2 and 3. So by performing a swap on a matrix B, I get a matrix C, a new different matrix, that this time this matrix is triangular upper, and this is the main diagonal here. So this will be very useful to compute the determinant of C. So now what I have is a cute upper triangular matrix C, for which it is super easy to compute the determinant. But what I want is the determinant of matrix A actually. So now the only thing I need to keep in mind is what was the sequence of elementary row or column operations that helped me transform matrix A into matrix C. So the operations were replacement, replacement, and swap. So determinant of a new matrix is equal to determinant of the old times, well, replacement doesn't change the determinant, so it multiplies by 1. Replacement doesn't change the determinant, multiply by 1. And the swap multiplies the determinant of the old matrix by -1. So here it is, with the color codes. So I have finally the determinant of C is equal to negative determinant A. Since determinant C is very easy to compute, this product of diagonal terms is 1 times 5 times 33, it's 165. Therefore, determinant of A is negative 165. So I get it from here. So that's how we can very quickly compute the determinant of an ugly matrix by transforming it using elementary row operations and just listing them and making sure that we know the formula. What's the link between the determinant of a new matrix, the cute matrix, triangular upper, and the old ugly matrix? We just need to figure out what are the numbers here. And those are linked to the fact that these elementary operations, for instance, replacement doesn't change the determinant, so we multiply by 1. Replacement doesn't change the determinant, we multiply by 1. Swap multiplies the determinant by -1. We could also be more opportunistic and not necessarily push to get a triangular upper matrix, because that also requires some work. So some people might use a combination of cofactor expansion and some of the elementary row or column operations. It's their choice, it's fine. So that's what I call hybrid approach. So in our previous case, where I had my matrix A and two elementary row operations brought me to matrix B, because these two elementary row operations are replacement, determinant of old matrix and determinant of a new matrix is the same. Now, what I observe is that my matrix B, okay, it's not triangular, but I have 2 zeros in a column 1, and I have 2 zeros in a row 2. So now I could be opportunistic and expand, let's say, by column 1 or by row 2. So I don't need to go and produce upper triangular matrix. I could, it's fine, but I could be more opportunistic from time to time. So this observation that I have 2 zeros in column 1 or 2 zeros in row 2 tells me, hey, I could expand by one of them. So let's say here I choose to compute determinant of B by expanding by column 1 of B. Somebody could choose row 2 also, it's perfectly fine. So in this case, we need to just remember the formula for the cofactor expansion. So it's -1 to power the coordinates here 1 plus 1, so that's why we have 2, times the value, which is 1, and then I eliminate column 1 and row 1. So I get 0, 33, 5, minus 11. So determinant of B is equal to -1 squared times 1 times determinant of this new 2 by 2 matrix. I compute, I get -65, 165. Well, that's the same result as previously. Since I know that determinant of A and B are the same from this page, because I used only replacement operations, and I noted this, very important to keep track of what's going on with the determinants. Since determinant of A is equal to determinant B, and determinant B is -165, well, determinant A is also -165. So that's a quick way to compute. So let's say I have, in another example, a 4 by 4 matrix, and there's no 0 anywhere in that matrix. So expanding by cofactor expansion would be long. So I need still to compute determinant, and then I go, okay, can I use some of the row or column operations to simplify things a little bit and maybe expand on a later stage? So here I observe in the matrix, and I'm lucky, I see that if I apply a replacement elementary row column operation on column 1, well, miracle will happen. So I can replace column 1 by column 1 plus 3 times column 2. It just happens that the numbers are such that this will work. Okay, when I do that, I used replacement operation, so that doesn't change determinant. So determinant of the original matrix and determinant of the new matrix is the same. But my matrix B, now it's much cuter because it has a lot of zeros in column 1. So this observation here helped me actually produce these zeros. That's why I did the operation. It's not obvious which operation you need to do. But in this case, well, by observing carefully, I figured it out. It's not always obvious that you'll be this successful. Maybe you will need to do a couple of operations to get there. But here I have 3 zeros in a column 1. So I'm gonna expand by column 1 to compute determinant of B. So I just copied B in the corner so we have it. So to find determinant of B, I need to expand by column 1. That would be the smart thing to do. So again, cofactor expansion, this is entry 3, 1, so it is -1 to power 3 plus 1, which is 4, times the value of the entry, 11, times the determinant of a matrix that I get when I eliminate column 1 and row 3. So here is the matrix C. So the determinant of B is 11 times the determinant of C, because I expanded. Okay, fine. So I have it here to keep in mind. So now I need to compute the determinant of C. Okay, there's no zeros anywhere. So I could apply 2 elementary row operations to kill -2 and +3 in the first column. That would help me. So these are the 2 elementary row operations that are replacement, and they do not change the determinant. So the determinant of a new matrix D and the determinant of old matrix C are equal. Oops. Now the good news is I have again first column with 2 zeros below the leading entry. So I can now expand again by first column. That would be a smart thing to do. So that's exactly what I'm going to do. Have my matrix D, I'm going to expand by first column, because I have 2 zeros here. So the determinant of D, again, by cofactor expansion procedure, I have -1 to power 1 plus 1 times the entry -1 from here. And then I eliminate column 1 and row 1. So times the determinant of this smaller matrix. I compute all that, I get 105. So now it's over, I got my number at the end. So now how does this number relate to the determinant of A? So remember all these red boxes? They are kind of important, all the red boxes. So now I come and I say, okay, the determinant of A was equal to the determinant of B. And then the determinant of B was equal to 11 times the determinant C. But determinant C was equal to determinant D, and determinant D was 105. So putting everything together is actually determinant of A is equal to 11 times 105. Compute. Determinant of A is 1155. Finished. So here it is important to keep in mind all these relations between determinants of different intermediary matrices. These red boxes, they are important. So you need to keep them, to keep track of what's going on, what's the relation at the end. Okay, so those are the ways that we have to compute determinant. So in summary, we have 3 options. We can do cofactor expansion. There's nothing wrong with it. It just could be long when we have big matrices that do not have any zeros inside. That would be very long. In that case, we could use another option, which is option number 2, where we actually try to transform our original matrix into an upper triangular matrix by using elementary row or column operations. And why upper triangular? Well, we know that triangular matrices, for them, it's easy to compute the determinant. So it could be upper triangular or lower triangular. It could be also diagonal, it's fine. But diagonal, you understand that you will need to work a lot for nothing. There's no point of trying to produce diagonal matrix. Upper triangular or lower triangular is just enough, because determinant for those is just product of entries on the main diagonal. And the last option is a hybrid approach, where we can say, okay, I will do a couple of those elementary row operations to produce a couple of zeros, and then I will use cofactor expansion, like we did for the last 2 examples. That's fine, there's nothing wrong with it, it's perfectly legitimate. So you can choose what you want to apply, when you want to apply it. It's all your choice and it's all correct. There is no wrong choice here. Whatever you choose, it's fine. It's you computing, and the method you choose will be fine. You have 3 options, you choose whichever one you like the most.